Relativity is one of the most scientific theory in 20th century. But how well does it explain the things we see in our everyday life? Formulated by Albert Einstein in 1905, theory of relativity, notion by the law of physics are the same in everywhere. Theory explains that the behavior of object in space and time. It also predicts everything from the existence of the black holes to light due to gravity to the behavior of planet Mercury on its orbit. The implication of Einstein's most famous theory are profound.
When Einstein put forward his general theory of relativity, that gravity itself is the bending of space and time by mass and energy, it was a seminal moment in the history of science. Today, the importance of his work is even better recognized than a century ago. First, there is no absolute frame of reference. Every time you measure an object's velocity, or its momentum, or how it experiences time, it's always in relation to something else. The speed of light is the same, no matter who measures it or how fast the person measuring it is going. Third, nothing can go faster than light.
If the speed of light is always the same, it means that an astronaut going very fast relative to the Earth will measure the seconds ticking by slower than an Earthbound observer, while time essentially slows down to the astronaut, a phenomenon called time dilation.
Electromagnets work via relativity as well. When a direct current of electric charge flows through a wire, electrons are drifting through the material. Ordinarily, the wire would seem electrically neutral with no net positive or negative charge. That's a consequence of having about the same number of protons with positive charge and negative charge. But if you put another wire next to it with a DC current, the wires attract or repel each other depending on which direction the current is moving.
Similar to gold, mercury is also a heavy atom, with electrons held close to the nucleus because of their speed and consequent mass increase. With mercury, the bonds between its atoms are weak, so mercury melts at lower temperature and typically a liquid when we see it.
Just a few years ago, most televisions and monitors had cathode ray tube screens. A cathode ray tube works by firing electrons at the phosphor surface with a big magnet. Each electron makes a lighted pixel. When it hits the back of the screen, the electrons fired out to make the picture move up to 30% the light of speed. Relativistic effects are noticeable, and when manufacturers shaped the magnets, they had to take those effects into account. If Isaac Newton had been right in assuming that there is an absolute rest frame, we would have to come up with a different explanation for light, because it wouldn't happen after all.